Hi, my name is Christina or Nina Aragon, and I'm a PhD student at Oregon State University. Today I'm going to be talking to you about using community snow observations, snow depth measurements, in order to improve our estimates of mountain snow. I was last here in 2019, and I'm very excited to tell you about all of the progress we've made since we were last here. And before I get started, I'd just like to acknowledge my collaborators, David Hill, Amelia Mayorga, Anthony Arendt, Gabriel Wolkin, Ryan Kremley, Katrine Wilkstrom-Jones, and Elizabeth Burikowski. I'm going to start this presentation with a little bit of background information and then go into a brief overview of the Community Snow Observations or CSO project and give you an explanation of why CSO data are so important. Then I will give an overview of how we use these observations to improve our models. And finally, we will take a look at our real-time snow distribution application. As most of us here are familiar, snow is wonderful because of the recreation opportunities it provides. There's nothing quite like pow turns and face shots. But seasonal snow also plays a vital role in the hydrologic cycle. It serves as a natural reservoir that bridges together winter water storage and summer water availability when both human and ecological demand is the highest. Despite the importance of seasonal snow, the distribution of mountain snowpacks are fairly unexplored in many parts of the country, with few on-the-ground observations available in mountainous regions. In order for us to understand how snow is distributed across our mountains, we need in situ or on-the-ground snow observations to serve as a reference point. These snow observations can be automated or manual. The image on the left shows an example of an automated snow telemetry or SNOTEL station. SNOTEL stations are at fixed locations and provide data at high temporal resolutions. SNOTEL stations are typically located in relatively flat, sheltered terrain that's easy to access by cars. Manual snow measurements, on the other hand, are made by individuals or teams of individuals, and while they're less frequent and regular in time, they can be done anywhere on the landscape. The relative lack of on-the-ground snow data available in high-elevation complex terrain is what motivated the creation of the Community Snow Observations or CSO project. CSO was launched in 2017 with the goal of developing a global network of citizen scientists who would collect and submit measurements of snow depth. While anyone can participate, the project has prioritized participation by backcountry recreationalists and snow professionals. These users have been prioritized since they frequent high-elevation regions of complex terrain where there are few on-the-ground data sources. Participation in CSO is easy. There are 3 simple steps. First, participants go somewhere in the backcountry. Second, participants will measure the snow depth. This is typically done with an avalanche probe since we all carry them as part of our backcountry gear. And third, participants submit their snow depth measurements via the Mountain Hub app, which is available on iOS or Android, or participants can upload their observations through the SnowPilot desktop platform. CSO data are publicly available for download at the communitysnowobs.org website, and you can also see lots of tutorials on taking measurements on our website. Okay, before we get into the modeling component of this work, I want to define one term. Snow water equivalent, or SWE, is a commonly used metric when we talk about snow as a water resource. SWE describes the depth of water one would get if they were to melt a depth of snow, and it is the product of snow depth and snow density. Great, so now we can talk about our snow model, which is called Snow Model. Snow Model is a physically based, spatially distributed snow evolution modeling system, and we can use this to model our snowpack evolution across each winter. The inputs to the model include weather, elevation, and land cover information, and then the model gives you out estimates of variables such as snow depth, snow water equivalent, or melt rate. These variables are modeled so that they are continuous across space within our defined modeling domain. In the animation that is playing, you can see the evolution of SWE across multiple seasons of SWE in our Wyoming modeling domain. While the snow model does a pretty good job of simulating snowpack evolution on its own, we can incorporate on-the-ground snow observations through a data assimilation process. Data assimilation compares modeled snow estimates to observed snow measurements in order to provide a correction factor for the model. In this figure, the dark blue line shows the estimated SWE if the model is run without including any snow observations. The red dot shows a CSO observation, and the blue line shows the trajectory of the snow model once we assimilate that CSO observation. You can see that the incorporation of this on-the-ground observation has helped to correct the modeled snow estimate so that it passes through that observed point. In most national-scale snow modeling efforts, observations from automated snow station networks, such as SNOWTEL, are the primary source of data that are assimilated into our snow models. From a mountain snow perspective, one shortcoming of these networks is that they are typically located in accessible locations that are not at risk of hazards such as avalanches. Because of this, many alpine and remote mountain areas are missed. And this is where the value of CSO observations really becomes apparent. CSO observations are unique in that they provide a source of in situ data in complex terrain where we typically lack observations from automated stations. In this image, we're looking at Teton Pass. There is one SNOWTEL station in this area indicated by the blue marker, and the CSO observations are indicated by all of those red points. You can see how CSO observations really fill in the terrain and the landscape, and one big takeaway here is that the places that are fun to ski are generally the places that we need data. So let's take a look at how data assimilation influences modeled SWE in our Wyoming domain using a case study from the 2018-2019 winter. In order to perform this analysis, we first divide all the SNOWTEL stations in the domain in half. One half of the stations is used for assimilation, indicated by the gold dots on the map, and the other half of the stations are used for evaluation, which are indicated by the blue points on the map. You can also see all of the CSO observations we used for assimilation indicated by the red pluses. We then conducted a series of numerical experiments that compared snow distributions for 4 modeling scenarios. 1, if no data were assimilated. 2, if only CSO data were assimilated. 3, if only SNOWTEL data were assimilated. And 4, if a combination of CSO and SNOWTEL data were assimilated. Through these experiments, we found that the assimilation of CSO data is of equal or greater value than the assimilation of SNOWTEL data. This is demonstrated through 2 key findings. First, the assimilation of CSO data improves modeled SWE estimates compared to snow model runs with no assimilation. And second, the assimilation of CSO data in addition to SNOWTEL data improves modeled SWE compared to the assimilation of SNOWTEL data at the majority of evaluation sites. This is really impressive considering that SNOWTEL provides regular SWE observations, while CSO observations were contributed opportunistically by citizen scientists and are relatively random in space and time. In Wyoming, we found that the overall top-performing runs assimilated a combination of CSO and SNOWTEL data. These plots compare the modeled SWE at 2 SNOWTEL sites, and they are both within our modeling domain. The y-axis shows the SWE depth, and the x-axis shows the day of the water year starting on October 1st. The red line shows what was observed at the SNOWTEL station. The dark blue line shows the modeled SWE if we do no assimilation, and the light blue line shows the modeled SWE if we assimilate CSO and SNOWTEL data. You can see that the assimilation of these data points improved the model performance by moving the modeled SWE line closer to observations. This animation shows the difference between the SWE modeled with assimilation and the SWE modeled without assimilation. Anywhere you see green is where assimilation increased SWE compared to the baseline snow model run, and anywhere you see brown shows where SWE was decreased by the additional assimilation of observations. Note that there is variability across the landscape in both space and time. Overall, the assimilation of these observations largely influences our modeled snow distributions. These experiments informed our data assimilation scheme for our operational product, which can be found at mountainsnow.org. We are really excited to launch this real-time web application because it is something that our participants have been asking for since day one. You want to know how much snow is out there, and we want to tell you. So let's take a look at our web application. This is the homepage for mountainsnow.org, and you can see each of our 9 modeling domains indicated by the black boxes in this map. Let's zoom in on our Wyoming modeling domain. The default setting for this map is to show you the most recent modeled simulation for snow water equivalent. You can also select different dates by clicking on this Jump to Date button on the left. And you're able to examine both satellite products as well as a variety of modeled results. There are multiple modeled snow variables that you're able to select here on the left. Or you can turn on and off layers by expanding this Layers tab on the upper right. The sliders next to each layer allow you to adjust the transparency. SWE is the default variable that's visible when you open up mountainsnow.org, and it is indicated by this color bar on the lower left. You can also view the snow depth, or you can view the 3-day change in snow depth through this platform. So now we're going to use the color bar on the bottom right, and so anywhere that you see shading in red, snow depth has decreased in the last 3 days, and anywhere you see shading in blue, snow depth has increased over the last 3 days. And finally, you can view the difference between modeled results that included observations and the modeled results that had no assimilation. So anywhere you see red shading here, the inclusion of observations decrease SWE relative to the baseline snow model runs, and anywhere you see blue shading, the assimilation of observations increase SWE compared to baseline runs. You can also turn on the satellite map for the base. It's often really nice to have this in the background and then adjust the transparency of the layers if you're really wanting to check out a certain zone that you're interested in. You can adjust the color bar of any of our snow variables by using the slider underneath each snow variable. This will adjust the maximum level of the color bar, and this increases resolution, especially when there's low snow levels. SnowDAS is the other modeled product that we allow you to view through the website, and you just select the SnowDAS checkbox in order to view that. And you'll note that it is a national scale modeled product, but it's at a much coarser resolution than the CSO product. And this becomes really important when you're looking at complex terrain like in mountains, because there is quite a bit of variability in snow distribution. So it's really fun to check all of these variables out. So I encourage you to jump on the website and just have a look around. And of course, none of this would have been possible without participation from all of you who are out there submitting snow observations. So thank you, sincerely. You're not only helping out your fellow snow people to know more about their mountain snow, but you're supporting science and helping us to better understand our water resources for downstream communities. So thank you. I'm happy to answer any questions.